welcome to CEC lectures. Myself Dr. Preeti Chagwani. I am an associate professor, Department of Computer Science, Aribhat College, University of Delhi. So presently we are learning this advanced data structures and algorithms, and in our previous lecture we have gone through disjoint set data structures, and within that topic we particularly explored about union find data structures. Now today's topic is about one of the very prominent applications of that union find data structures, which is nothing but Kruskal's algorithm. About this Kruskal's algorithm we have discussed in a very brief manner in our previous lecture. Today we are going to get a detailed insight about this Kruskal's algorithm, why when this Kruskal algorithm is used, what is the application of this, and specifically we are going to throw the light on this Kruskal's algorithm from the point of view of union find data structure. To be specific, that in implementation, where are we going to use this union find data structures, which we have studied completely in our previous lecture. So just give you a recap in a nutshell. Please help me let me help you recall that union find data structure is actually a data structure which is about querying about the connectivity, which is used to query about the connectivity in a particular graph. So this is what the basic idea behind this is, and if we talk about the operations which are supported by this data structures, they are make set. That means each and every individual element will be a set and all the sets will be singleton. Then we will be saying union of two sets, which is more commonly known as union A comma B, and then we will be looking for the representative element or the set representative for a particular element. That means, so for example, if I am going to say find A, that means it will reply or it will respond in the it will respond for the representative element of the set to which A is belonging. So these were kind of three operations which are prominent and are to be used with union find data structure. So make set X, then union A of two sets which we call as union A comma B, and then we have find A or find any element which will return the representative element. Now in our previous lecture we have seen that Kruskal's algorithm is going to be one of the applications of this union find data structure. So Kruskal's algorithm is basically an algorithm for finding the minimum spanning tree. And what is minimum spanning tree? And one of the methods of this minimum spanning tree, that is Prim's algorithm, we have already discussed in a lecture series of algorithm. So Kruskal's algorithm is also there for finding the minimum spanning tree. So minimum spanning tree says that for a graph you need to visit all the vertices and the sum of the edge weights of all these vertices should be minimum. That is what our minimum spanning tree is. So when we say Kruskal's algorithm is going to use this union find data structure. So Kruskal's algorithm, in this the given graph will be considered as a forest, and every node which this graph is comprising of, you can take them as individual trees, and a tree, that is a single node, is connected to another only and only if it has least cost among all the available options. Also it must not violate minimum spanning tree properties. So when we say that a node will be connected to another if and only if it has least cost among all the available options. So for example, there is a connectivity between A and B, and there is also a connectivity from A to C and then from C to B. So whichever is kind of having the least cost to reach to B, either it is a direct one which is from A to B, or an indirect one that is from A to C and then from C to B, whichever is having a least cost, that will be taken to be included in the tree. Also it must not violate minimum spanning tree properties. So, one of the property of minimum spanning tree is, as we are considering a tree, it should not result in a kind of cycle. So, Kruskal's algorithm, when we see in detail, is having some steps. So, the first step says we need to sort all the edges in non-decreasing order, or to be precise, increasing order of their weight. So, there are different edges, we are going to sort all those edges, and these edges will be sorted according to their weight in an increasing manner. Then we will be picking the smallest edge and check for the cycle formation. So, in some initial steps, it is not kind of it is not an issue unless it is a self edge. So, there will be no cycle formation, but every time we are going to pick an edge, we will be checking for the cycle formation, and then we will include the edge only if cycle is not formed, else we are going to discard it. This is one of the properties of minimum spanning tree, as I have told you. And then we will be repeating this step 2, which is picking the smallest edge and checking for the cycle formation and inclusion if edge is not being formed, until there are v minus 1 edges in the spanning tree. So, why I am talking about v minus 1 edges, because there are v number of vertices, and if till the point there are v minus 1 edges, it will be considered as a tree, and after this v minus 1 edges, definitely a cycle will be formed, and the tree will be kind of converted to, we can say, graph or something. So, yes, it is it is important to keep a tab on this v minus 1 total number of edges. Now, Kruskal's algorithm, as you all must have judged by this time, that this is a greedy algorithm. That means, what is the greedy technique, or what is the greedy choice which Kruskal's algorithm is adopting? That is, at each step it is going to add the next lowest weight edge that will not form a cycle to the minimum spanning the forest which is built so far. And at the termination of the algorithm, the resultant forest has a single component, that means it will result in the form of a tree and forms a minimum spanning tree if the graph is connected. So, here is a disclaimer that this is going to result in a single component at the end, obviously at the termination of the algorithm, because in the middle of the algorithm, it may have some components and it may not result in a single connected component, but at the end, at the termination of the algorithm, yes, the resultant forest will have a single component and forms a minimum spanning tree if your input graph is connected. So, this is what the disclaimer with Kruskal's algorithm is. Now, let us try to see the we can say flow of this Kruskal's algorithm in a step by step manner. So, here is an graph which is given on the screen, and please notice that this is an undirected graph, and we have seen in our previous lecture that this union find data structure is going to be used only for undirected graphs, not for the directed graphs. So, here you can see that we have given edges and also we have given weights, and please note that these edges are written according to the increasing weight. That means the weight of AD and C is 5 each, then comes their DF which is 6, then AB which is 7, BA also 7, BC, FE are 8 each, and EG and DB are 9 each, then FG is 11 and DE is 15. So, now what are we going to do? We will pick the smallest edge first, include that into a minimum spanning tree. Initially our minimum spanning tree is, we can say, blank. So, include that, and then we keep on picking the edges and adding it to minimum spanning tree only with the condition that they should not form a cycle. So, let us start with AD, that is the first edge which we are going to kind of add into our minimum spanning tree. Then we have CE. Now C is altogether a different edge and AD is altogether the different edge. So please imagine the minimum spanning tree consisting of two edges as of now. So one is AD, weight is 5, so is C and E, weight is 5, and both are kind of we can say these two components, one is AD and another one is CE, are two trees of the forest. So that is what I was telling, that within the middle of the algorithm, that before termination, we can say your algorithm may have different components, not a connected component. So that is possible. So we have included AD, we have included CE also, and we have also checked that this inclusion of CE is not creating any cycle into this AD. Now coming to DF. So DF also we are going to include, as it is not forming any cycle, if you can say. After that we have AB. So AB is having the weight 7, that is also fine. So we can include that as well. Then coming to BE. So BE as of now is not forming any cycle, we will be adding that as well. Then now here it is, if we are going to add BC. So we already have a CE, we already have a BE, that means if you consider that triangle, so we have we can say the two edges of the triangle, and if we are going to put BC here, then it will result in a cycle. So that means whatever the edges which are remaining, that is BC, FE, EG, DB, FG and DE, despite of having the minimum weight among them, we are not going to include this BC, because this is going to kind of result in a cycle. So let us see this step. So first of all, you can see this AD in a different color. So we have included AD at the first step, the weight is 5. Then at the second step we are going to include CE. Now you can see these two edges in different colors, no cycle formation is being given, is being happened till this point. Then after that we have DF, which is having the weight 6, that is the next in the increasing order of the weight. So DF we are going to add. So here you can see all these three edges colored in a different color. Then after 6 we have the next weight as A, B and BE, both are there, and they both are having the same weight, which is 7. So we have included AB. So till this point we have included AD, we have included CE, we have included DF also, and we have included AB, and all these edges you can make out in different colors. Now after this step, the next edge which is available according to the increasing weight is BE, that is having a weight 7. So now we need to check that whether this inclusion of this BE is going to result in a formation of a cycle, then we will discard it, else we will take it. So here presently I am not able to kind of witness any cycle here by the we can say inclusion of BE. So BE also we have included. So now we have AD included first, then we have CE, DF, then we have AB, and then we have BE. Moving forward, the next weight which is coming is 8. So with 8 we have two edges, two different edges with the weight 8, that indicates, and we also had two different edges with weight 5 as well and 7 as well. So this indicates that it is not necessary to have unique edge weights here. So now let us say if we are going to add BC, then this inclusion of BC will result in a cycle of BC and E. So obviously we are not going to include it. Another edge which is of the weight 8 is Fe. Now if you include Fe, then that Fe will also result in a a cycle, and that cycle will be A, B, E, F, D and A again. So that is going to be a cycle. So with the weight 8, we are discarding in a way kind of both the edges. Now both the edges discarded, let us move on to the next edge weight. Next edge weight is 9. So here we have dB. So if dB is to be included, that will again create a cycle which is A, B, D, that will form a cycle. So here we are discarding dB as well. Now the next thing which is available, or the next edge which is available with weight 9 is EG. So we can safely add this EG, and also we need to keep a tab on the number of edges. So EG we have kind of added. So here you can see all those edges which are included in the minimum spanning tree in a different color as they are. So after 9 we can see that are there any vertices which are not covered, or to be kind of more precise, what is the number of edges, what is the number of vertices. So if you can see, the number of vertices we have is, how many vertices we have? We have 7 vertices here, and the number of edges, so we have 6 edges which are already included in this minimum spanning tree. So vertices are A, B, C, D, E, F and G. So total 7 vertices, and if there are 7 vertices, we are looking for 6 edges. So we have AB, we have AD, then BE is there, CE is there 4, then DF is there 5, and there is EG. So 6 edges are there. So ultimately we have, what does it indicate? This indicates that we have covered all the vertices present till this point without kind of, we can say, forming a cycle. Now the moment we are going to add one more edge into this will result in the formation of a cycle. So this is going to be our minimum spanning tree, so which is having all the vertices and V minus 1 number of edges. So this is what is required as a minimum spanning tree. But unless we look into the details of the implementation, we will not be able to see that where exactly our agenda data structure, which is nothing but the union find data structure, is going to come into picture while implementing this Kruskal's algorithm. Here is kind of, we can say, another example for running this Kruskal's algorithm. I am not going to run it completely because the focus of this particular lecture is not the kind of running or not the dry run of the Kruskal's algorithm, but the implementation level details with the which should focus on this union find data structures. So with this graph, if you want to generate your minimum spanning tree, something of this sort I can say will be kind of generated. So now let us look into the algorithm, and then its we can say time complexity analysis, and let us see how the usage of this union find data structure is going to kind of affect the overall time complexity of this Kruskal's algorithm, if we say in. So pseudocode here we have F is actually kind of a set, we can say. Presently it is phi, and for each vertex belonging to G of V, we have individually called a make set, and this is the step of the Kruskal's algorithm when I said that the graph given is a forest, and we are going to kind of break into, or we are going to generate individual trees which are nothing but the singleton sets and having all vertices. So make set is going to do the same thing. All these V vertices are in the form of individual we can say individual singleton sets. And now there is a for loop which says that for each edge belonging to G dot E ordered by weight u comma v, in an increasing manner, of course, we are going to look for the representative element of the sets to which these two vertices of the edge belongs to. So, find set, so let us say edge is u comma v, then we will be looking for find set u equals to find set v. Now, if find set u and find set v are is the the same component, is the same representative. So, find set u will give you the representative of the set to which u is belonging. Find set v will give you the representative of the set to which v is belonging. Till the singleton sets, each and every set is having its own is having only one element, and that element is the only representative there. Now, if find set u not equals to find set v, then we will add this edge u comma v in our set F, which is actually your ultimately going to be your minimum spanning tree. So, basically find set u not equals to find set v is actually checking for the presence of cycle. If u and v are both belonging to a same component, then that means again adding an edge u comma v within that component, within that connected component, will result in a cycle. So, we are going to add the edge only if there is kind of we can say no cycle formation, which is going to be checked with the help of find set u and find set v. Now, when this is added into the graph, that means we need to add them into that minimum spanning tree, and for that we have called the operation union, which is union of find set u and find set v. That means the two different set to which u and v are belonging are actually connected, or we can say we are combining them, we are making a union of them. So, here if you can see, we have used all the three operations of your union find data structures. One is make set v in order to have a forest of trees, and every tree is in the form of a singleton set. Then in order to check the presence of cycle, we have used find set u and find set v, and in order to combine the components, we have used union of find set u and find set v. So, with the help of this union find data structure, the task of implementation of Kruskal's algorithm has become we can say a lot simpler. Now, yes, this was kind of we can say pseudocode, or you can say more specifically this was an algorithm of your Kruskal's technique to find minimum spanning tree. If we want to kind of make out the time complexity, if we want to calculate the time complexity, so let us have a look on the time complexity itself. So, time complexity says we need to sort the edges by weight by using any comparison based sorting algorithm, and the best which we can do in worst case is E log E, because E is the number of edges, basically number of elements for this. So, we have order of E log E time we have spent for like what we can say sorting the edges, and after sorting we will be removing the edges with minimum weight, or we can say we will be picking the edges with the minimum weight. This operation can be done in a constant time. Now, a disjoint set data structure is used to keep a track of which vertex belong to which component, and that is done with the help of the representative component of the set. So, we are going to place each vertex into its own disjoint set, that is making V trees, and this is going to take order of V operations. So, total time is till this point is order of E log E time, or equivalently we can say order of E log V time, where you are aware that E is the number of edges in the graph, and V is the number of vertices. So, we have taken kind of a track of that disjoint set data structure. Now, let us say E, considering a dense graph or something of that sort, E is at most square of V. So, for example, there are maybe let us say kind of let us say 8 vertices. So, there can be at most 64 edges, and taking a log both sides. So, we have log of V square is equals to 2 log V, or we can say order of log V. So, E can be kind of replaced with log of V, and each isolated vertex is a separate component of the minimum spanning forest that we have seen, and we are ignoring isolated vertices. We are going to obtain V is always less than equals to 2E, or we can say log of V is equals to order of log E by taking log on both the sides. Looking into the implementation level details, we require that disjoint data structure set to achieve the desired time bounds. So, after sorting, we are putting vertex into its own tree via V calls to make set function. Then we are iterating through all the edges, and for each edge we determine whether the end belongs to different trees. This is going to use 2 find set calls, and every find set call is order 1 each. For union of 2 trees for which this union set data structure, disjoint set data structure union set function will be called, that is order of 1. So, if we sum up the whole we can say time complexity, it is going to be order of E log V plus V plus E, which is considering the asymptotic notation, we can say order of E log V. So, that is going to be the complexity when we are using these calls to make sets, these calls to kind of we can say find set, and calls to union also. So, this is going to be an kind of with the simple disjoint set data structure. This can be done, this whole operation or this whole implementation can be done in E log V time, order of E log V time. So, here if we talk about the summary of the lecture, we started with the recap of union find data structure. We looked into de Kruskal's algorithm. We have taken a dry run of a Kruskal's a graph to generate the minimum spanning tree, and then we have seen where this union find data structure is going to play a role in the effective time complexity of this Kruskal's algorithm. This is all from my side for this particular lecture. I will see you in the next one. Till then, take care. Goodbye.